So what we're going to do in this lecture is we're going to come up with an equation that provides us with system derivatives for a control volume formulation. If you recall, we talked about in the last segment how the basic laws, so the law of conservation of mass, linear and angular momentum, and energy, are derived for a system of fixed mass. But in fluid mechanics, we always deal with fluid in motion, and consequently it's difficult to deal with the fixed mass thing. So we're going to come up with a way to be able to take the time rate of change, or the derivative of those four different properties, and be able to express them in a manner that we can apply to fluid mechanic analysis. So before doing that, I'm going to define both an extensive and intensive properties, and those will be for mass, momentum, and energy, and then we'll move ahead and come up with that derivative equation. So the extensive properties that we're going to be dealing with, I mentioned mass, momentum, moment to momentum, and energy. And we can also define an intensive property, which is what we will put into our equations. So the intensive property is just the extensive property per unit mass. And what we're going to do, we're going to express this property as an integral across the system that we're looking at. And so we can integrate the intensive property if either across the mass or across the system. And the properties that we're looking at are for the four governing equations or basic laws. Okay, so those are the intensive and extensive properties for our four basic laws: conservation of mass, linear momentum, angular momentum, and energy. And what we're going to be working on is coming up with an equation that enables us to express the time rate of change of any of those properties with respect to time rate of change, so with respect to time, but expressing it in terms of the control volume formulation. Okay, so we're after a way to be able to express this time rate of change for any of our system properties in terms of a control volume. And so in order to do this, what we're going to begin with is a schematic. And what the schematic will show is a control volume and a system that coincide in time at t0. But then later in time, what will happen is the system will continue to move because there's fluid flow in the system that we're looking at. But the control volume will remain fixed in space. And we're going to use that as the basis for our derivation of getting that d by dt of whatever the property we're looking at in terms of control volume variables. So let's begin by looking at our system and control volume at time t0. So what we have here is we have time t0 where we have a system and a control volume that coincide and occupy the same chunk of mass. But what we're going to do, we're going to have it where the system is moving and the control volume is fixed in space. And so it is not moving. And now what we're going to do, we're going to redraw this at a later point in time. So this will be time t0 plus delta t. And we want to look and see what has happened to the system and the control volume. We know control volume is going to be fixed, but the system will have moved off and to the right. So let's resketch that and take a look at what it looks like. Okay, so what we show here is the control volume, as I said, was fixed. It's not moving, but the system is. The system is occupying the fixed mass. And what we're going to do with this is we're going to assume that there are three regions. The first region is region 1, which is defined by the boundary between the control volume and the system. Then we'll have region 2, and this will be again bound by the system on the left and the control volume on the right. And then finally, we're going to have region 3, and that will be defined by the control volume on the left and the system on the right. And what I'm going to do is I'm going to write two little differential volumes or elements, one in region 1 and one in region 3, and that's where we're going to be focusing some of our analysis. So let's begin with the differential element in region 1. And the second differential element we're going to look at is over here in region 3, and I'll call that subregion 3. So that's subregion 3 in region 3, and we're going to be looking at those in further detail. So there you can see that this is a schematic that we're going to use when we come up with the formulation for the time rate of change of our properties and be able to convert it between intensive and extensive. And you know what I'm going to do? Let me just clean that up a little bit. These lines should really be parallel to the streamline, so I apologize for that. My artistic abilities are not great. Yeah, that's a little better, but not great. So anyways, there's region 3 and region 1. Okay, so with that, what we're now going to do, recall what we're after is a way to be able to express the time rate of change of whatever intensive property we're looking at from a system into a control volume. But let's begin by defining that as a system. And what I'm going to do is I'm going to say that intensive property, whatever it might be, if it's mass, momentum, or energy, I'm going to define it as N, capital N, with a subscript capital S. And so we can define the time rate of change in differential form. So this is a definition of the time rate of change, and what I'm going to do is I'm going to call this equation 1. And this is going to be the equation that we're going to build from as we go through this derivation. And what I'm going to begin with is looking at what is happening to our intensive property or extensive property at time t0 plus delta t. So, and I'm going to refer to our schematic in coming up with this expression, but we want to know what is contained within our system at t0 plus delta t. And so referring back to our schematic, this would be the figure on the right-hand side that we're looking at. And at t0 plus delta t, what we see is our system is defined by the black region around that encompasses region 2 and region 3. And consequently, we can write that as being our intensive or extensive property. In this case, it's extensive because it's capital N. So it's what is in region 2 plus what is in region 3 at time t0 plus delta t. Now, what I'm going to do, I want to write this in terms of the control volume, and so I'm going to make a substitution here for what we have for region 2. And looking back, we can see that region 2 consists of its part control volume. So we can take what is within the control volume minus what is in region 1. And so let's do that. And this here is equal to the extensive property in region 2. And then adding that to what is in region 3, and that is all evaluated at time t0 plus delta t. So we have that. Now, another thing that I'm going to do, this is where I'm going to start bringing in the intensive property. So if you recall earlier, we said that the extensive property could be evaluated by an integral over the system of the intensive property times rho dV. So I'm going to make that substitution for each of the terms in this equation here, and what we get is the following. So this gives us an expression for this is what we're showing here. So that gives us the value of the extensive property at T naught plus delta T for our system. And we have a little bit of the control volume and then regions 1 and 2. So that's what's happening at T naught plus delta T. Let's take a look at what is happening at time T naught. So at time T naught, the control volume and the system were overlapping with one another. So we can say that our system value, our extensive property at T0, is also equal to what was happening in the control volume at T0. And so this we can represent as an integral across the control volume of eta rho dV at T0. So if you're wondering where we're going with this, what we're working on is we're trying to evaluate the different terms in equation 1. And we're going to make some substitutions as we work along. So there we have what is happening at time T0. And now what I'm going to do is I'm going to take these and I'm going to plug them back into equation 1. Okay, so and this is all divided by delta t because we're plugging this into equation 1. So what you can see, we have a little bit of a mix of things at T0 plus delta t. We have some things over the control volume and some things of region 1 and region 3. I'm now going to rewrite this equation and I'm going to break it into things that are either control volume, region 1, or region 3. So let's go ahead and rewrite it. Okay, so our equation is getting cleaner and cleaner. That's a joke. Now what we're going to do, I'm going to take this and I'm going to call it A. And that's the thing that had only control volume integrals. Then I'm going to take this here and I'm going to call it region or equation B. And then I'm going to take this one here and we're going to call it equation C. And so what we're going to do, we're going to try to simplify or re-express each of these one at a time. But what you'll notice right off the bat, this one, A, involves only control volume. B involves only region 3. And C involves only region 1. And so if you remember, we had those little differential elements in region 3 and region 1. We're going to be using them for understanding what's going on in B and C. Control volume, we'll use what's going on in the control volume to get the first part. So let's work our way through A, B, and C, and then we'll try to simplify this equation, make it look a little neater and more presentable. So in the limit, as delta t goes to 0, what you'll notice that we have in the expression for A, this here and this here, that's just the value of n evaluated for the control volume at either T0 plus delta t or T0. So that's just the time rate of change of the property n in the control volume, which we can also express in the following manner as an integral over the control volume of our intensive property times rho dV in order to get the mass. So that takes care of A, so that is good. We have A figured out. So that's A. Now let's move on to